I'm going now to present you a technique which is going to be used in conjunction with the partial dynamic reconfiguration to try to reduce the overhead introduced by the reconfiguration time. I'm going to refer to this technique with the name of B-stream relocation. Let me first define some concepts used within the example I'm going to use. We have 6 functionalities, A, B, C, D, E, and F, represented with a node that have to be implemented on the FPGA. To properly characterize our functionalities, we need to assign to each of them an execution time. Now, just to give you an example, we know that the functionality labeled as B is identified by 2 numbers, 1 and 2. 1 is referring to the number of reconfigurable regions needed to implement that functionality, while 2 is the quantity of time units needed to complete its execution. Let us now consider the FPGA. At least at the beginning of this example, we are going to consider it as an homogeneous device that has been partitioned in 3 reconfigurable regions in a monodimensional way. Furthermore, all the 3 regions are defined exactly in the same way. Each functionality to be implemented needs to have a physical assignment. This means that to properly create the corresponding B-stream, I do have to assign to each of the functionality a region, or a set of regions to implement it. Within this context, I'm considering the case in which a functionality can span more than one region if needed. One thing which is important to notice is that to create a configuration B-stream, we have to define all the functionality reconfigurable regions mapping. This is a crucial step in the design of a reconfigurable system, because we may generate structural hazards at runtime because of the subsequent call of 2 functionality sharing the same reconfigurable region. Let me better describe this problem. We know that we have 6 functionalities that have been implemented on our FPGA via their corresponding partial reconfiguration B-stream. In this example, we do not have any data dependency between the 6 functionalities. In other words, we can see this as a set of 6 services that are going to be requested by a pool of users. Within this context, we are working under a blind scenario. A blind scenario is a context in which the functionality will be requested without any specific order, but the needs of the user at runtime. I'm defining such a scenario as a blind one because we cannot predict when a functionality will be requested. Within this context, we are assuming the following sequence of calls: A and B, C, D, E, and F. With such a sequence of calls, given our mapping decision, even by using a partial dynamic reconfiguration, we cannot do better than the execution proposed in the figure. A and B can be configured together on the FPGA because they are not sharing any reconfigurable regions. As soon as the C service functionality is called, it has to wait for A to complete its execution because of the structural hazards on reconfigurable region 1 and reconfigurable region 2. And now we can observe an interesting scenario. Even if there is no data or control dependency between C and D, the D service cannot be configured on the FPGA as soon as it has to be requested. We do have enough available resources to host it, but because of the mapping decision we took, we have a structural hazard between services C and D on the reconfigurable region 2. The same thing is happening when the E service is called. It has to wait till the completion of the execution of D to be configured on reconfigurable region 2. Now, the problem is quite clear. Because the functionality reconfigurable regions mapping decision we made, we are delaying the overall execution time of the system. Is there any way to deal with such a problem? The answer is obviously yes, and the idea is quite simple. We are going to implement each functionality on each of the feasible reconfigurable regions. We know that the 6 functionalities are all different. We know that from the implementation of a functionality to another one, we may need different resources, but we are working with a simplified model where all the reconfigurable regions are identical. Within this context, the feasibility check for a mapping solution is quite simple. We just need to have enough adjacent reconfigurable region to implement the desired service. The figure is presenting all the possible implementation for each functionality. Now, we can implement a better runtime. As soon as D is going to be requested by a user, we do not have to wait for the completion of C any longer, but we have to check 2 things. 1. Do we have on the device enough available resources to implement D? Second, do we have an implementation of D based on the set of available resources? If the answer to both these questions is yes, as it is in our case, we can then proceed with the reconfiguration of D. This is obviously a great improvement in terms of the overall execution time. But what if the number of services is going to be higher than 6? What if the number of reconfigurable regions is going to be larger than 3? This scenario can be catastrophic because of the explosion of all the reconfiguration bitstream necessary to cover all the different possible solutions. We do need something different. That is exactly the rationale behind bitstream's relocation technique. The idea is quite simple. We have just one implementation per service functionality. Now, do you remember what, at the end of the day, a reconfiguration is all about? It is the storage in the configuration memory at the proper addresses of the configuration data. Now, if all the reconfigurable regions are identical, this means that relocation a service from one reconfigurable region to another is nothing more than storing the corresponding configuration data into the proper set of addresses. This implies a terrific improvement in performance. The bitstream's relocation technique increments the overall speed up of the system execution. It reduces the amount of memory used to store partial bitstream, and it allows a runtime assignment of the bitstream placement.